Hi, this is Mr. Phillips, and I'm going to help you with Activity 5.2. In the first part of this activity, you're going to focus on the magnetic cannon, and in particular, you're going to look at the part of the magnetic cannon that consists of the ball that rolled in, contacted the two magnets, and then transferred its energy through to ball E, which is the last ball, launching it out away from the other part of the system. So I have that part highlighted with a red rectangle here, and we're going to refer to that part as the assembly. And remember, it was sitting on top of the rail, and then we had Earth's force at distance pulling down on it. Ball E is the last ball, and that's the one that shot out very quickly as ball A contacted the magnets. One of the activities we did, we drew a force model of all of this, where we had all of the arrows, so we could see all the forces acting at once. And we'll come back to this force model. It'll probably help us out a little bit when we draw our free body diagram. Now for question A, it says, what happens to the assembly of the ball bearings and the magnets that do not go flying when the last ball shoots out? Well, we talked about this already, so I thought I would just give you the answer for this one. The assembly, again, highlighted in the red rectangle, moved backwards very quickly, but only a very short distance, whereas ball E moved very quickly in the opposite direction and went down the track extremely fast. For part B, what they want you to do is draw a free body diagram of the assembly of the balls and magnets that do not go shooting out at the moment that the cannon fires the ball, ball E. If you need some help, you were supposed to look back at the free body diagram you made of the shooting ball in Activity 3.3. So I have a lot of information on this screen that I'd like to talk to you about. So up here we have our force model showing all the forces acting on the entire assembly as well as the rest of the system, including ball E, the rail, and the interaction with the Earth. So we have our solid contact force arrows in pairs, and we have our force at a distance arrows in pairs, both for gravity as well as for the magnetic force, going all the way through here and from here to here. Down here what I did was I drew a free body diagram of what happens just before ball E leaves. So this is before ball E leaves. So this is just a moment. So we notice we have the no motion sign up here. So we have the assembly up above, it's in a red rectangle. And as ball E exerts a force as it gets ready to launch off, we have several forces going on here. So we have ball E pushing against the assembly. We have static friction fighting against the force that ball E is exerting on it. And then we have our two vertical forces between the rail pushing up and the earth or gravity / weight pulling down. At this moment, all these forces are equal and opposite, equal in strength, opposite in direction. Therefore, they're canceling each other out, so the assembly is in equilibrium, or all forces are balanced. Now, when we get down to this one, I have a lot of stuff going on here that I want to talk to you about. So this is just as ball E launches. So what we have going on here is we have our assembly. We have our two vertical forces, just like before, with the rail pushing up, earth, weight, and gravity pulling down. But notice we have our start of motion arrow here. And so what I did was, I have my static friction. Now I put it on this side to demonstrate that there is a net force. So my static friction was started on this side originally. And notice the static friction arrow is longer than the dynamic friction arrow. And we know that once the object starts moving, there's less friction on it than getting it to move. The static friction is a greater force than the dynamic friction at any given point. So what happens is, as soon as ball E pushes back on the assembly to launch, the static friction is overpowered, and we end up with a net force with the remainder of the ball E force. And so the net force is pushing back this direction on the assembly as the ball launches. So it overpowers the static friction, so we have an unbalanced force. And as a result, as the assembly is moving to the left, dynamic friction is pushing to the right, trying to counteract its motion. So as I move on here to the next picture, you'll notice I've cleaned it up a bit and I've gotten rid of some arrows, because if we're looking at it just as the magnetic cannon fires, ball E is now gone because it's already pushed off. So the forces acting on the assembly now, the vertical forces, we have the rail pushing up, earth gravity weight pulling down with the force at a distance. And then the only other horizontal force to slow down the assembly is the dynamic or kinetic friction, which it will cause this to slow down and eventually stop. Now this happens extremely quickly in our magnetic cannon. So now we have some questions to answer. The first question is letter C. What makes the assembly of ball bearings and magnets move backward, away from ball E? So take a moment to study the diagram and try to answer this question. Alright, so what makes the assembly of ball bearings and magnets move backwards away from ball E? Well, it's a backward horizontal push, contact force, from ball E that makes the assembly move backwards. The two horizontal forces acting on the assembly is the force of ball E pushing back, initially, getting it to move, and then the static friction with the rail. Now once the ball E force overpowers the static friction, then we have a net force to the left, which causes the assembly to begin to move. The larger force is an unbalanced or net force from ball E, which again causes the assembly to move backwards, and then the counteracting force we'd be left with would be the dynamic or kinetic friction. For question D, it says, which force is greater, the force that makes the assembly recoil or the force that makes ball E shoot out? So pause the video, take a moment, and answer the question. Again, we have a lot of information in our graphic to look at, but if we pick it apart, what we'll figure out is that, according to Newton's third law of motion, the two forces acting on the assembly and ball E are actually equal. They're an equal strength, magnitude forces, and the reason why we end up with a net force is because eventually we end up with ball E pushing onto the assembly, but the force acting on the assembly is stronger than the static friction, which is pushing back against ball E, allowing the assembly to move backwards due to the net force caused by ball E. The ball E moves faster and farther than the assembly does because it has a smaller mass and lower static and dynamic kinetic friction. Therefore, ball E, even though it's the same force pushing this way as what the assembly was pushing on it this way, ball E goes out further and it appears to have a net force because of the fact that it's much smaller mass, and so as it pushes this way, once it overpowers that static friction, remember the dynamic friction is a much smaller force, creating a net force of movement to the left. It's a bit complicated. Now for part E, the question says, why does the assembly recoil only a short distance and then stop? So try to answer this question, pause the video. Alright, the answer to this one is, when the collection of the balls and magnets moves backward, in other words the assembly, they're subjected to only one horizontal force, which is the dynamic or kinetic friction on the rail, or with the rail I should say. So remember the assembly is sitting on the rail, so the only force opposing the motion is the dynamic or kinetic friction pushing to the right, whereas the assembly is moving to the left. The force of ball E is no longer existing because ball E is now gone. It's left this part of the system, and so therefore ball E is no longer in contact with the assembly. That means the only force acting horizontally against the motion is the kinetic or dynamic friction, which is then going to cause this assembly to slow down and eventually stop. And that's it.